This is section 3.3, page 7. We'll start here with problem number 9. Now look at this equation here. We have this equation. There's a relationship between the variables p and q such that this equation is true. So p equals ABR over q minus AB minus the quantity Ca squared over q squared, where A, B, R, and C are all constants. So that means that they're numeric values. They're just the placeholders for them are the letter, but you need to think of those as like a constant. A times B times R is some constant. We just don't know what it is. Okay? The problem asks us to find dp dq. This is very similar to dy dx. Right? So the function is p, and then the variable of interest is q. So this is the derivative of function p with respect to the variable q. dp dq. So your variables in your function name can actually be any letters. So we're going to treat q like it was an x, like it's, that's our variable. And then p is just our function like our function y. So what do we have here? We actually have two separate terms separated with a subtraction. So we know that to get the derivative of this, we can just find the derivative of the first term and then subtract the derivative of the second term. So that would be my plan. So dp dq. So let's just look at this first piece here. I would use the quotient rule here. So let's start with that. The quotient rule, you always start with the bottom. So we have q minus ab times the derivative of the top. Since these are all constants, the derivative of any constant is 0. So this is times 0. Minus the top, which is ABR, times the derivative of the bottom. The derivative of the bottom with respect to the variable q would just be the coefficient of q, which is 1. AB is just a constant, so its derivative is 0. So the derivative of q is 1. All over the bottom squared. So q minus AB quantity squared. That's the first piece. Now we need to do the derivative of the second piece. And since it's minus this derivative, I'm going to go ahead and put my minus sign. And I always like to be very careful with my negative sign, so I'm going to block off the rest of this so that eventually I can distribute that negative sign. Ca squared over q squared also requires the quotient rule. So I'll start with the bottom, q squared, times the derivative of the top. Ca squared is purely a constant. So its derivative is 0. Minus the top, Ca squared, times the derivative of the bottom. So this, since q is our variable of interest, we're going to use the power rule here. 2 in the front, 2 moves down to the front, the variable stays the same, and we subtract 1 from the power. So the derivative of q squared is just 2q. Just like the derivative of x squared is just 2x. Alright, all over the bottom, q squared squared. Okay, so that's what I have. Now I just need to simplify all this. And the first thing that I know I can get rid of is this term times 0 makes that 0. That times 0 makes that piece 0, so it's already simpler. So here we go. This is just, the numerator here is now just minus ABR. Denominator stays the same. Q minus AB squared. Over here, my numerator, I have a minus Ca squared 2q, and if I distribute that negative, this makes it positive. So I'm just going to say plus. And I'm going to put these in order. My numerics need to be first, so it's 2Ca squared q all over, and this would be q to the 4th. Okay, we're almost done. There's really no value in making a common denominator between these two. That would just actually make it a little more complicated. So instead of that, I'm just going to look to see if there's any other thing that can be reduced or simplified. There's nothing in the first term. In the second term, I have a q and a q to the 4th, so actually I can eliminate one of the q's, change that to q to the 3rd. And it looks like that's all I'm going to be able to do. So I'm just going to rewrite it with that one last change. Q minus AB quantity squared plus 2CA squared over Q to the third. This is dP dQ. Okay. Next is a word problem. I like this one. It's a perfect time of year for it as well. A pumpkin farmer. He currently has 150 pumpkin plants, and they each yield 8 pumpkins per plant. And this is per year. Of course, we only produce pumpkins once a year. He's expanding his pumpkin patch at a rate of 15 plants a year, while improved husbandry, which is improved farming techniques, he actually increases his annual yield by 2 pumpkins per plant. So he's got 150 plants, 8 pumpkins per plant. He has an improvement of 15 plants a year. He has an additional improvement of 2 pumpkins per plant. The question is, what's the current instantaneous rate of increase of his total annual production of pumpkins? Anytime you see instantaneous rate of increase or instantaneous rate of change, we're talking about a derivative, or the slope of the tangent line. Okay, so to answer this, I'm going to need to get, first of all, a function that represents annual production, and then I'm going to need to take the derivative of it. So let's establish some variables here. I'm going to let P equal my annual production. That's what I'm interested in, looking at the instantaneous rate of change of. I need a variable for time. I'm just going to conveniently use x. So x is the year number, or the number of years that have passed here. And I just want to think in terms of, in words here, what do I have? I need an expression for annual production. And if you think about it, annual production, spelled it wrong, annual production would be basically the number of plants that you have times the number of pumpkins that you get per plant. Okay, so the number of plants times the number of pumpkins per plant would be total number of pumpkins produced. Okay, now I need to make an equation for all of this. So annual production, I already decided I was going to use the variable P for this. Number of plants. So we look back to the word problem and see what we have. We start with 150 plants, but it doesn't stay fixed at 150. We add, we add 15 plants per year. So we're going to add 15 times whatever year it is, so 15x. That would be 15 plants per year. So at year 0, we have 150. At year 1, 165. At year 2, 180, and so forth. So that's the number of plants we have. Times the number of pumpkins per plant. So we start out the process yielding 8 pumpkins per plant, but then we're going to improve every year, and we're going to add on 2 pumpkins per plant per year. So that's going to add on 2 times t. So in the, not t, x. I don't have any whiteout, so we're going to do this. Sorry about that. So 2x. So in the first year we have 8 pumpkins per plant. And after 1 year it's 10 pumpkins per plant. At 2 years it's 12 pumpkins per plant, and so forth. So if we take a look at this equation, we actually have a couple things happening. We have an increase in production just based on the number of plants. We have an increase in production based on the pumpkins per plant. So we got 2 things changing at once. So I already planned out that I needed the instantaneous rate of change, which would be the derivative of this function. So I need P prime. There's actually a couple ways to get it. I could FOIL this out, because it's just a binomial times a binomial. I could FOIL it out and get one expression. Or I could use the product rule. That's what I'm going to do. I'm using P prime. This would also be denoted as dP dx. If you use t for time, dP dt, whatever you happen to use. So I'm going to use my product rule. Product rule starts with the first function, 150 plus 15x, times the derivative of the second one, which is just 2, plus the second function, 8 plus 2x, times the derivative of the first, which is going to be 15. And that is my equation. I need to distribute. So I'm going to distribute my 2 to both of those places. That gives me 2 times 150 is 300, plus 2 times 15 is 30x. I'm going to distribute my 15 next to these two pieces. 15 times 8 is 120, plus 15 times 2x is 30x. And now just combine like terms. Let's see, 420 plus 60x. That is the equation for the instantaneous rate of change, or the slope of the tangent line of p, for any value x that I choose. The problem asked for what is the current instantaneous rate of increase. So current, that is x equals 0. So I simply have to evaluate p prime at 0. So I get 420 plus 60 times 0, which is just 420. So I have an increase of 420 pumpkins per year. Okay. Anytime you're doing a word problem, you should definitely put units of measure in here. And actually, I should write a full sentence on this. So that's what I'm going to do. I'm going to say, give it context. The number of pumpkins is increasing. Oops. So we want to say whether it's increasing or decreasing. In this case, it's increasing at a rate of 420 pumpkins per year. And then you also have to state when this occurs. So this would be at the current year. If I had picked anything other than 0, well, let's just say I picked 1, just for fun. That'd be 420. At the end of the first year, what's my rate of increase? It would be 420 plus 60 times 1, so 480. So I would say at the end of 1 year, the number of pumpkins is increasing at a rate of 480 pumpkins per year at the end of year 1. So it's just extra, no extra charge.